Hello, Year 10. We're coming close to the end of our section on electricity now, and there's really just one lesson left to do on electricity, which I'm going to try and cover now. And that's basically looking a little bit at mains electricity as opposed to electricity that you get from a battery or a cell. So, what's the difference between mains electricity and the electricity you get from a cell? Well, the first thing obviously is the voltage, the potential difference is much higher, which is why mains electricity is regarded as more dangerous. You can possibly get a fatal electric shock from mains electricity. But there is another difference as well, which is that mains electricity is something called alternating current as opposed to DC or direct current. Now, what do we mean by alternating current? Well, as the name suggests, alternating current means current which goes backwards and forwards along a wire rather than flowing in one direction. So whereas a cell obviously has a positive end and a negative end, and it will just push current one way around a circuit, alternating current, a mains electricity supply, will push current backwards and forwards. So there isn't a positive and negative terminal when you're talking about mains electricity, because they would swap over continuously all the time to move the electricity backwards and forwards. Now you may wonder, well, what's the point of current going in both directions? Well, for one thing, as we'll learn next year when we do magnetic induction, generators produce alternating current electricity naturally. And the other thing is if the current is alternating quickly enough, you won't notice that it's an alternating current. A light bulb will light up whichever direction the current flows through it. So if the current's just going backwards and forwards continuously, the light bulb still lights up. And most electrical components will work absolutely fine with alternating current electricity. A little bit about alternating current electricity and mains electricity. First of all, the little demonstration which I've got down here is about fuses. We'll come to fuses in a minute. Let me just talk you through plugs and wiring in mains devices. So what I've got here is the cable which is from the end of an extension lead, and the plug's been taken off it. And what you can see inside this cable is 3 wires. Okay, there's a red or brown, I should say brown wire. They did used to be red, but they changed it a few years ago to brown, the standard colour. The brown wire is the live wire. Okay, the blue wire is the neutral wire, and the one that's sort of got green and yellow stripes is called the earth wire. Now let's ignore the earth wire for a minute. Okay, I'll worry about that in a minute. It's these 2 wires that deliver the electricity, that deliver the power to the device. Now, obviously, these 2 will go into, the plug's been taken off. I'll show you what the inside of a plug looks like in a minute. But the 2 prongs here are the live and the neutral. Okay, that one there is the neutral, that one there is the live. But I'll show you inside a plug in a minute. So it's these 2 wires that deliver the electricity. So the potential difference between them swaps from being one of them being positive, one of them being negative to the other way. But actually, the neutral wire, this one, we say that has a 0 potential, and therefore the live wire is the one that's actually got the alternating potential. So in the UK, that wire will stay at 0 volts. This wire, the live wire, will change from about plus 325 volts to minus 325 volts. So really, it's the live wire that's pushing and pulling current from the neutral wire. Imagine in your device, these will be connected, in a circuit. Okay, and when that's positive, it'll push current that way. When that's negative, it will pull current that way. Okay, so that's the live and neutral wires. So they deliver the electricity, the electrical energy to the device. Now let's have a quick look inside a plug and see what we can see. Now it did used to be on the syllabus that you had to demonstrate how a plug was wired up. And I always thought that was quite a useful task, because sometimes you do have to wire plugs. It's not very often these days, because a lot of devices, well, most devices you get do come with plugs on them. But actually, I had to wire a plug up just the other week. And the reason for that is I bought a pump for a fish pond that I have in my garden, and it came with a long 10-meter cord, but it didn't come with a plug on the end, because I think they assumed that you'd have to feed the cord through a hole in the wall, in my case to the garage, and then fix your own plug to the other side. So indeed, I did have to actually wire it up. It's the first time in quite a while I've had to wire up a device. But in the old days, I'm talking really old days now, when I was your age, if you bought an electrical device from the shop, it wouldn't come with a plug on it. Kind of amazing, but you would have to buy your own plug and put it on. Okay, so I seem to remember as a kid getting a Scale Electric set at Christmas and then being disappointed that the power supply didn't have a plug on it. And then we had to sort of frantically search for a plug to put on it. Anyway, I'm going to show you what's inside here. So this is the inside of a plug. And the first thing is all plugs have a sort of cable grip to keep it nice and tidy, and to make sure none of the exposed wires inside are pulled out to the outside. Okay, so that's the cable grip. This is all made of insulating material, by the way. Okay, the cables themselves are made of insulating material. The housing of the plug, insulating material, because you don't want to get a shock. The only thing that's not insulating, of course, is the prongs. Okay. So the neutral wire goes into this prong here. So that one. So the blue one goes to the left. The brown wire, the live one, goes into this prong, but it goes through a fuse. So this sort of cylindrical thing here, which you can take out and replace if you need to, if it blows, is a fuse. Okay, and it has a wire inside, and this is what I'm going to show you on this little demo here, that blows when a certain amount of current flows through that live wire. Okay, that's going into your device. So in this case, it's rated as 10 amps. That's actually quite an unusual sized fuse. The standard sizes for fuses are 3 amps, 5 amps, and 13 amps. So it's been quite a while since I've seen a 10 amp one. So that is a slightly unusual size fuse. But basically, if a current of more than 10 amps flows in that live wire, that fuse will blow. Okay. The final wire was the earth wire. Again, I'll talk a bit more about earth wire in a minute, but the earth wire connects to this prong on the top here, this big one. Now, in fact, not all devices have earth wires fitted. Okay, they don't need earthing. So some devices will only have the brown and the blue wires fitted inside the plug. Okay, so that's basically how a plug is wired. Okay, if you ever have to wire a plug, basically each of these prongs has a screw that unscrews, and then you slide the wire in. The wire has to be shaved at the end so that the copper on the inside is showing, and then it goes into each of the prongs, and then you tighten up the screws. They're pretty easy. They're pretty straightforward. Okay, obviously I wouldn't recommend that you do any mains wiring yourself, but one day when you're adults you may have to. Okay, you may buy a pump for a fish tank like I did, and have to fix your own plug. Okay, so that's how you do it. Right. Okay, so I'm just gonna put that back together again. So what I'm going to show you now, just very quickly, is a fuse and how a fuse works. Now, fuses are kind of obvious. They are thin pieces of wire that are designed to melt and break when a certain amount of current flows through them. So this is what I've set up here. what we've got is a piece of wire. Okay, I've actually taken it from a pan cleaner. Okay, in the kitchen. It's like a piece of steel wire. I've connected it to an ammeter, and just out of view of the camera over here, I've got a power pack. So what I'm going to do is I'm going to turn this power pack on, and we're going to put some current through, and we're going to try and see at what point this wire will blow. So inside that fuse, that 10 amp fuse that was in the plug, there was a, although you couldn't see it, inside there was a very thin wire. Okay, so right, so we can see the current that's flowing here, so 0.7 amps, so not a huge amount of current so far, and although I can actually feel some heat coming off the wire, it's not glowing yet. So let's turn it up a bit. Okay, 1.57 amps, still not glowing. There we go. Okay, so can you see what's happening here? 2 amps, and that wire is glowing. And if I turn it up any more, at some point, it's going to... There we go. And it melted. I didn't actually read what the current was when it melted. But at a certain value, you can see there it's actually stuck onto the plastic. Oops, actually reconnected it there. At a certain value of current, it did actually melt. Okay, and that's exactly how a fuse works. Okay, you might wonder about the value of the current when it's alternating current, because I mean the one in this plug says 10 amps. Does that mean 10 amps in either direction? Well, no, and this is something that you don't need to really understand or know about at this stage, but for alternating current, there's kind of like an average value of current that's worked out. Actually, if the current was changing from +10 to -10, this average value of the current, which is called the RMS current, is only about 7 amps. Okay. So there's an average value, and what the 10 amps there means on the fuse is that it's this average value has to be more than 10 amps, which means it would have to be changing between -14 and +14 amps on the live wire for the fuse to blow. But that's something that you don't really have to worry about at this stage. Okay, it's basically just remember that above a certain current, the fuse breaks. Why is it on the live wire? Well, it's because it's a live wire, if you remember, that's actually doing the pushing and the pulling in the circuit. It's the one that's changing from a high potential to a low potential, whereas the neutral wire is fixed at a 0 potential. So if you kill the live wire, you kill the device essentially. So you cut off the electricity supply to the device. Why would you get a large current flowing in the live wire? Well, one reason why is you could have a short circuit in the device. So internally, the live wire inside the device could have come free and then touched another part of the device, and you've got a short circuit. Therefore, you've got a huge current flowing, and it could be moisture that's got in the device, and that will then trip the fuse. There's another reason why the fuse might break as well, and this is where this earth wire comes in. Now, I said earth wires they're not actually connected to all devices, but they are connected to some devices. If a device has got a metal outside, so the exterior could be a metal kettle or something like that, or a power tool. If a device has got a conducting exterior, then the most deadly thing that could happen is that there's a fault inside the device and the live wire touches the outer casing of the device, because then any person who touches the outer casing, the electricity will conduct through the casing into them and then down into the ground, and at mains voltages it would quite possibly kill them. So this is where the earth wire comes in. So the earth wire, obviously, it goes in there into the wall. and then there's a wire in the wall that goes down into the ground from the earth wire. In the device, obviously the earth wire goes up the cord of the device. The earth wire will be attached to the outside of the device, to the metal outer casing of the device. And then what happens is, if the live wire comes unattached in the device and touches the outer casing, there will be a very low resistance route for current from the live wire to go through the earth wire and then through, obviously, that prong and then straight into the ground, into a copper spike that's under your house. And that will produce a huge current which will trip the fuse. It will break the fuse. Okay, so before anyone even has a chance to touch the outer part of the device, if the outer part of the device becomes live, you'll have a huge current flowing down the earth wire, and the fuse in the live wire would break. So it's an added level of protection. If you've got a device which is completely insulated on the outside, I mean, I don't know, possibly if I just move this up here, my power pack there looks like it's sort of got a plastic casing there. So this could be a good example. A device that's perfectly insulated on the outside probably wouldn't need an earth wire connected, because you're never going to get a shock if there's a short circuit inside, because it's not going to touch the outside, or it's not going to get through the outside. So that's why we have earth wires. So that's it. That's the wiring inside mains devices. So you have to learn the colours of the wires, the fact there's a fuse on the live wire, what the role and the purpose of the earth wire is, and also you have to know about what alternating current is as opposed to direct current. So those are all the sort of learning points. I'm going to give you some notes on this to do this week and put into your exercise book. There's also some notes as well on the national grid. Now, we do more on the national grid next year when we talk about transformers. There's a little bit this year that you have to understand. The national grid is the way that mains electricity is distributed between the power stations and people's homes. Okay, so there's a little bit on that. And that is basically it for domestic electricity. Okay. If you've got a different textbook that's not from this syllabus from the AQA, you may have something about circuit breakers, which are another safety device that you can have with mains devices, but that's not on this particular syllabus. Okay, so that's it. We're going to set you some work, and also there'll be some homework, and that homework, I think I'm going to ask for it to be in by, should we say Tuesday? Okay, actually we're on Saturday today. Okay, let's say Wednesday. Okay, we'll give you till Wednesday to have a go at that work, and we'll see you obviously in the Zoom lesson next Friday. Okay, one or two of you didn't turn up to the last Zoom lesson, so make sure you're there. Right, okay, so that's it. Have a good weekend.